exact values in trigonometry. Now, before I go much further, I quickly want to remind you what trigonometry is again. If we have a triangle, which is a right angle, we have theta, this is opposite, this is adjacent, this is hypotenuse. Then my trigonometrical functions is the ratio of these sides towards each other. In other words, if I say the sine of theta, the sine of an angle is opposite over hypotenuse. I'm not going to go into details. Watch previous videos if you forgot this. But this is opposite over hypotenuse. And let's just quickly look at the sine of theta. If I then start with a triangle with an angle of 1 degree, and I know that's bigger than 1, I say that's opposite over hypotenuse. And I can see that this opposite over, sorry, this is the adjacent, that's 1 degree, that's adjacent, and this is radius. Opposite, adjacent, hypotenuse. I can see that opposite over hypotenuse is going to be a small value. As this angle gets bigger and my hypotenuse stays the same, okay, I can say that this becomes closer to 90. This opposite over hypotenuse is getting bigger and bigger and bigger. Okay, that ratios are not very easy numbers to work with. And before we had calculators, they actually had printouts. So I'm talking about even up to the 60s and 70s, people didn't have calculators that can calculate the sine, cos, and tan of angles. They actually used books that looked like this, and I had all these values that has been printed. So if I was looking for the sine of 9 degrees 45 minutes, well, I had to go to this booklet, scroll through the page, go to 9 degrees, go to 45 minutes, see which one is sine, and then get that value. All of these values are rational approximations. Okay, I'm going to quickly illustrate to you what happens. So if I have this on my calculator, go clear, escape, clear, second function, clear, clear. If I go table and I put in my function y equals sine x, enter, I say start at 0 and I step up 1. My calculator is in degrees, that's that little DEG, it says DEG, so it's in degrees. So I enter, 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 enter. It means when this is then x here is my angle and this is my sine. I can see that these values are very hard to work with. These are the values that you found in that booklet. And if you go through them, and I'm going to quickly, you see all of them looks like that, because the ratio, as this angle is getting bigger, this side is getting bigger, and as it's getting bigger, you can see the ratio is also getting bigger. Okay, we're 12 degrees at 0.2, and it goes up and up, it goes up and up and up as I go on. And it goes and does that all the way. I always see something funny. At 3 degrees, it doesn't have any repetitive decimals. It is exactly a half. And you can go through, it doesn't happen in the sine at all, again, all the way up to 90. So from 0 to 90 degrees, and we only can do sine, cos, and tan from 0 to 90 degrees triangles, it only happened once that we have exact value for the sine of theta. And if we investigate it a little bit further, we are going to find that this happened. We said when this angle was 30 degrees, the sine was opposite, was a half, 1 over hypotenuse, 2, which means I've got two sides of a triangle, and I could then use Pythagoras to then say, well, C equals the square root of 2 square minus 1 square, which is the square root of 3. So this becomes square root 3. And instead of using all those tables or using all these values that I calculated with my calculator, I could just find 30 degrees by using this special triangle, and I don't have to use my calculators. So this is very useful many years ago when they did have tables, and I wanted to explain to them all the identities and things that we still have to learn about trigonometry. Instead of using those tables with all the decimals and writing all the decimals, they could only use these values to prove all of the identities and all of the equations and things that we're still going to do. With us, it's a little bit easier, but yet, if we can use exact values without the use of a calculator, we can explain and we can also prove some of the equations and identities. The other angle, so it happened at 30 degrees, and if that is 90 degrees, then something happened at 60 as well. So they found that also at 60 degrees, on this list, if I would do this with the sine, with the cos, it happens only one place, and that is at 60 degrees because 60 is 1 over square root 2. And when you do it with tangent, it happens at one place only. And it happens only when this side is exactly as big as that side. Now remember, as I make this angle bigger and bigger and bigger and bigger and bigger, so from very small to very big, at some stage this and this is going to be exactly the same size. And that happens when this is 45 degrees. So when it's 45 degrees, the tangent was 1 because the opposite side is just as big as the adjacent side. So, and I can then find this side by using Pythagoras and saying this is 1 square plus 1 square, which is the square root of 2. And that's the two exact values, or the thing that you have to do. Some textbooks wants to teach you tables and things to learn. You have to learn the following. You have to learn and get yourself into writing every time the same thing, because you need to show this for communication marks. 30 is the small angle, 6 is the big angle, the smallest side is 1, hypotenuse 2, and the adjacent side of 30 is 3. So I can then find sine, cos, and tan from these triangles without remembering any tables. I just have to remember the diagram. And then the same with the 45. 45, all I have to remember is 1 square root 2. The other thing that you also need to remember now is, since we are moving away from only using degrees, they can ask you the questions in either degrees or radians. And then you just have to remember that 30 degrees is pi over 6, 60 degrees is pi over 3, and 40 degrees is pi over 4. So it's the same triangle, you just need to remember which one is which one. All questions that leads from here, you can only use this exact value graphs, diagrams, but whenever you are going to use them, you have to use this as part of your explanation. So that needs to be there with every question.